Hi, sorry for that delay. Technical problems in a tech conference, who would believe it? So without further ado, we now have Stefan Fanuka, who would talk to us about enabling real-time computing in OpenStack. Thank you.
Good afternoon. So yeah, talking about a real-time presentation, and we're now running on time, so I'm going to speed through this a little bit. Stop me if I happen to, there's a laser pointer at the end of this, so stop me if I happen to point the laser in somebody's eyes by mistake. So a little bit of background. This is a pretty broad presentation that covers a good few technologies, so I'm going to give a quick run through of some of the technologies I'm going to be talking about here first, and then I'll move into like a deeper dive on this functionality, how this is implemented and how it works. So in case you haven't heard of it, OpenStack is a big deal. It's an open source cloud computing system made up of a load of load of individual projects that focus on various aspects of a functioning cloud. So you have services for networking, you have services for compute, you have services for block storage, and so forth. The thing I'm going to be talking about here today is Nova, which is the compute service. I'm an OpenStack Nova core developer, basically one of the maintainers. And most of my focus on OpenStack Nova is on enabling NFV functionality, so high performance compute, huge pages, CPU pinning, that kind of thing, which I'm going to go into here. OpenStack, from a high-level perspective, it tries to be as much of a cloud as possible, so you should realistically never have to know anything about the underlying hardware capabilities of the cloud that you're running on. You're able to create servers, you're able to create networks, images, attach everything together. It's all nice and kind of like abstract and cloudy, and that's what 90% of people are looking for. But the problem with this kind of cloud abstractions and that is when you get down into the nitty-gritty of the kind of features that telco users or scientific users are looking for, those cloud abstractions tend to hamper your performance, and that's not something that you want. It basically means OpenStack isn't useful for your use cases. So we've been working on kind of fixing a few of these issues for, I'd say, since before the Juno release, which was 3 or 4 years ago. So we've implemented a couple of features during that time to kind of close this performance gap with like normal bare metal. So things like allowing you to attach SR-IOV devices to instances, allowing you to pin the CPUs of your instances to host cores, huge pages, like representing your guest topology in like a NUMA-aware fashion. And then the last 2 releases, we've worked on 2 particular features, one of which I'm going to talk today, the real-time policy, and then another one which I'm not really going to focus on, which is emulator threads policy. So for anyone that isn't aware what real-time means that if you have a real-time application, and you're guaranteed that that will meet certain timing constraints. So if you're delivering messages over a network, that those messages will be delivered at a certain amount of time. Something will happen like on a given repetition. It doesn't mean that it's fast or anything. It just means that it's consistent. And this is important from, again, the telco perspective, because if you're talking about sending voice packets or something over your network, you need to make sure that they actually get where they're supposed to be getting. So there's a couple of prerequisites for what I'm going to be talking about here. The first of these is that you need suitable hardware. This is a bit of a tricky area, because if you go onto like the real-time Linux kernel wikis and stuff, they'll list hardware and they'll say, well, we tested on this hardware and the performance wasn't that great and it was better on this particular chip than this chip. And they very rarely give a reason for why it's better. There's just something in the underlying architecture of those chips that makes it better for real-time use cases. all of the testing that I did on here was on a standard like Intel Xeon based micro semi server or something like that. Obviously, you're going to need OpenStack Pike or newer because, as mentioned before, this functionality wasn't available before Pike. You're going to need a recent enough version of libvirt because this all hooks down into libvirt deep down. And then you're going to need a kernel that has the real-time preempt patches applied. So CentOS packages this. You can get Rail versions of this. I don't know about Ubuntu. But I did all my testing for this on the CentOS 7.4 distro. From the host configuration, the hardware level, when you're benchmarking a system, these same kind of things come up. You want to disable kind of like fancy features, so power management, things like turbo boost and that. You want you don't want any magic going on in your hardware. You don't want it throttling the CPU because it decided that, oh, we're going to save you a little bit of power. You want it running 100% of the time. So basically disable hyperthreading, power management, turbo boost, that kind of thing. And then from the software perspective, the real-time kernel that I mentioned before, the real-time KVM module, and there's a utility called tuned, which will configure like your grub kernel boot parameters for you. Tuned comes with profiles for real-time that you can install through repositories, and that will just pass through those kernel boot parameters. So installing the kernels, installing the tune profiles, configuring those tune profiles, enabling huge pages, and then this last option, does this work? No. This last option is a Nova specific thing which lets you determine what cores on your system Nova is allowed to touch. When you're talking about real-time Linux, you should usually leave a couple of cores for non-preemptible processes. So the preempt patches make most things in the Linux kernel preemptible, but not everything. So the general best practice is to leave a couple of cores that the scheduler can keep for itself. So yeah, basically isolating a couple of cores from Nova. To guess what you're actually going to be running from your application perspective is entirely dependent on what you're trying to do. For the sake of testing, I just went and used the exact same configuration for my guest as I had on my host, so that meant that I was using the real-time kernel again, and the tuned profile, only this time I went for the guest profile, which again is it's packaged and available. If you already have a real-time application, whether that's something that you've got from, like, you bought in an application from Ericsson or something, a VNF, that kind of thing, then you should obviously use that. And again, install all those stuff, enable the profile, enable huge pages. And then we actually finally get into the OpenStack stuff. OpenStack Nova has two ways of configuring a guest. The first of those is via image properties. So when you create an image, you can set certain properties saying, I need this specific CPU feature for this image to work. The other way is what they call flavors. So flavors dictate how much memory your VM is going to have, how much CPU is going to have, that kind of thing. It also allows you to use a thing called extra specs, which are like scheduler hints. So they'll say, I want CPU pinning, I want real-time to use these cores, this kind of thing. There's three things that we're going to want to configure here. The first of these is CPU policy, which dictates whether your guest cores are pinned to the host or not. We're going to want them pinned. The second of these is whether you're enabling real-time. Because it's a real-time demo, obviously you're going to be enabling real-time. And then the last of these is huge pages, which you'll usually want from a performance standpoint. You've also got the other two things, but again, I'm not going to talk about these today. So going back to that OpenStack, the command line client, we're creating a flavor. We've got 4 CPUs, 4 gigs of RAM, 20 gigs of disk space, and we're giving it a name, RT1 small. And then we're going to set these extra specs, which again are like scheduler hints. So there's 4 of these here. The first of these, the CPU policy, is the one that determines whether your guest cores are pinned or not. Dedicated means that we want our guest cores to be pinned to the host cores. So there'll be a one-to-one mapping between guest core processes and your host cores. The second of those, real-time, we want to enable the real-time, and we also want to tell Nova that some of those cores shouldn't be marked as real-time cores. Again, because we're using the Linux kernel for our guest here, and we want some of those cores to be non-real-time and for scheduler processes. And then the last one is 1 gig huge pages. And then we create a server with this flavor and with some sample image that doesn't really matter. So the interesting thing about how this works, this only works, Nova supports a couple of hypervisor drivers. This only works with libvirt KVM. So if you're using Zen or something, sorry, you're out of luck. So what's interesting to look at here is the libvirt XML that Nova will generate for you, and what that actually, how that reflects, like deep down, what kind of calls and stuff it's making to the host. So the first of these is the CPU tune element. This will be, if you do like dump XML for your libvirt domain, you'll get a big XML blob with all the information about your guest in it. If we look at just the CPU tune one, CPU tune, it's an element that specifies which of your host physical CPUs that a main vCPU would be able to do. So that CPU pinning that I was talking about, this determines that for you. So there's two important attributes to note here. The first of these is the vCPU pin one and the vCPU scheduler one. vCPU pin, how that works under the hood, it calls a Linux function, which is set affinity. If you look at your QEMU process and you look at the threads that QEMU has spawned, it has an individual thread for every single one of your guest cores. So each vCPU is basically a host process, a KVM process. And by configuring this property, what we're saying is that the first vCPU in the instance, we want it pinned to core 2 on the host. We want the first vCPU then to be pinned to the third core on the host, and so forth. And libvirt calls the set affinity function on that. And if we go and we look using the taskset command at the pinning information for these cores, we see that in fact they are actually affine to host cores, and nothing else, if assuming you have your host configured correctly, nothing else should be running on these, which means that you're getting essentially 100% of your performance for each of your guest cores. The other one then is the vCPU scheduler attribute. So this is, again, another optional element, and what this determines is the scheduler type that your CPU threads are going to be using. Under normal circumstances, this will just use the standard scheduling process that whatever your host is using. Naturally, we don't want that. What we want is we want FIFO or one of the real-time priorities to be applied. How that works under the hood is, again, another kernel function. This time, the previous one was set affinity. This is set scheduler. And as the name suggests, you pass in a process ID and you tell it what scheduler policy you want to be applied to that process ID. And various magic will happen, and that will get applied. And for this, to validate this, we have a CHRT application. You pass in a process ID to this, and it'll give you the scheduling policy that's in order and the scheduling priority. The priority is a value from 0 to 99, and that determines if you've got two things and they're conflicting, which of those will take priority over the other process, naturally enough. The interesting thing to note here, the first two cores that we had, we're using, like I said, we had told we'd mask those because we didn't want every core in our guest to be running with a real-time policy because the kernel isn't necessarily guaranteed to work that way. So they're using the standard other policy for this. And then the other two cores, which is where if we were running an application, this is the cores, the guest cores that we would actually run our application on. They're scheduled with the FIFO policy. We also talked about huge pages. As far as that's implemented, there's a memory backend attribute. You say what page, we configure what page size we wanted, and then there's some other stuff in there that doesn't really matter. Nova does all of this for you. And if we go and we look at, again, the QEMU process, we get the process ID for that, and we look through the huge page mapping for each of those processes, we'll see that it is actually indeed mapped to the QEMU process as we'd expect. Because we created the server, if we go and log into that server then, you can use an application called cyclic test, which will evaluate the real-time readiness of your system. That'll give you a measurement of your latencies. From what I've been told, you want to be looking for something in the below 20 microseconds, I think, of latency. On average, anything below 20, you're usually pretty good. You wouldn't expect this to ever hit 0 for using the real-time preempt patches in the kernel. You might, if you had your own real-time application, a VNF or something from a telco, but for the kernel patches, you're not going to see that kind of thing. So yeah, a wrap-up. From a usability perspective, today, if you go and you install OpenStack, you configure your host correctly and you're using a recent release. You create your flavor, you set your various flavor attributes, and then you boot your instance, and you now have real-time compute within your cloud, wherever that may be. So yeah, that's keeping it real-time. Thanks for listening. If anyone has any questions, shout. Can you say that again? So, if I heard you correctly, you're saying if you boot multiple instances and they're pinned, they'll use the same host, they'll be pinned to the same host CPUs. Do we do anything to prevent that from happening? We use... Yes, so from a Nova perspective, the recommendation that we have is if you have pinned instances and non-pinned instances, the non-pinned instances aren't aware of the pinning information and they'll just stomp all over the cores. They'll float across cores and they'll use anything that they can. The recommendation we have for that is to use a Nova feature called host aggregates, where you essentially divide your cloud into multiple parts, and you're saying this part of my cloud, i.e. these servers, are allowed to run real-time processes or pinned processes. These ones are allowed to use non-pinned processes, and that just stops them from overlapping. If you have two pinned processes, Nova will make sure that the two servers won't overlap. There'll be no overlap. So you'll give 4 cores or whatever to one server, and then if you give 4 to another guest, there'll be 4 different cores. And if it's not able to do that, it'll fail to schedule. So it'll make sure that we don't overlap. That doesn't happen.
Well, what are the drawbacks of using real-time once someone decides to use dedicated CPU policy? What's the drawback of adding real-time except, let's say, configuration, and then the fact that you need to negotiate with your guests that fact?
So the question was, what are the drawbacks, if you have CPU pinning already, what are the drawbacks of adding real-time to that? So I know that there are performance impacts of using real-time within the kernel. Real-time, I think I said that at the beginning, real-time doesn't necessarily mean faster. It just means it's more deterministic. So the general recommendation would be you'd use real-time if your application requires real-time, knowing that it is going to require more resources or you're going to get less throughput. If you don't require that real-time, you shouldn't need it because you're better off increasing your resource utilization if possible.
So in the benchmark, you did stress on the guest.
Yes.
Did you stress on the host or on the other guests as well?
So the question was, in the benchmarks, did I stress the guest, did I also stress the host and other guests, did you say? Yeah. So as part of the deployment process for this, the expectation is that you would stress the host first to make sure that the host is actually configured. So there's a real-time evaluation tool, RT-eval, which you're supposed to use to make sure that it is configured correctly. And then you use something like cyclic test to make sure that your latency is what you'd expect. Yeah, so that was done before anything else was deployed on top, just to make sure that the host kernel was configured.
Right, but in this benchmark where you claimed that you got 20 microseconds.
Yep.
So the question was, did you at the same time when you stressed at the guest, did you make the test?
I did not. No, I didn't. No, they were separate processes. That would actually be a nice test to do. Because theoretically, there should be no impact. Theoretically, yeah. But I imagine there probably would be some impact. You'd be trying to keep as much logic. Even the way that I deployed this, I used, this still isn't supported in OOO, like Red Hat's deployment tool, so I was using DevStack for this. And it was an all-in-one deployment, so I had like Neutron and stuff running on that compute node. I shouldn't have had any of that there. They were all isolated, but realistically I should only have had the compute service running on that, and everything else should be on a different machine. It would be that's actually something I'll probably go and do when I get home.
Did you also try running 2 real-time guests?
I did. Did I try running 2 things? I did, but I didn't benchmark it. It was only just to make sure that it did work and there was no funky stuff going on. So the question was, if the VM is pinned to one CPU, is it possible to live migrate to a different host? No. Sort of. This is a long-standing bug with Nova. We don't provide, as part of a live migration, for anyone that's not aware, means that your instance is running and you move it onto a different host and the instance stays running with minimal downtime, like microseconds. It's usually a little more than that, but almost no noticeable downtime. The problem with how we do live migrations is we don't pass sufficient information as part of the live migration request to recalculate the CPU mapping on the destination side. So what ends up happening is that you use the exact same cores that you're using on the source on the host. We don't regenerate that, which means if you already had an instance running there and the cores you were using cores 5 to 10, and this used cores 3 to 7, then there would be the 2 or 3 core overlap. Yeah, so it's a long-standing bug, and the reason it probably hasn't been fixed is because the fix is really, really difficult.
Sorry, in that case, the scheduler of Nova doesn't select proper compute host, so it doesn't analyze the CPU utilization of all target compute hosts in order to find the good one, the suitable target.
So you're saying that the scheduler isn't properly evaluating the destination. It's a dumb, like how it's doing it is a little bit daft. All it's looking at is, do I have enough free CPUs? And it will attempt to find the pinning information. And if you have enough free CPUs, it's not a scheduler issue per se. So you will have enough free CPUs and it's able to do the appropriate mapping. But when it actually gets there, it doesn't recalculate that. So it's not the conductor. I can't think of the name of the actual specific service that would do that. But it's only the fact that we should be regenerating this XML and we don't. It's a long-standing bug and it's annoying, but the recommendation usually is like don't live migrate instances with pinning. And realistically, if you have CPU pinning on and you're worried about determinism and that, you probably don't want to be live migrating in most cases. It is a bit of a niche use case. Any other questions? I think we're good. Thanks, guys.